Page 392, number 31, is different for a couple of different reasons. One, we don't have linear equations or nonlinear equations to describe our border. Instead, our border is described to be a triangle with the following vertices. Let's go ahead and plot those vertices and talk about how to change and adapt our strategy to reflect that. The scale is a little bit larger, but we're going to define this to be 1, 0. We're going to define this point right here to be 2, 1. And then 1, 1 is going to be right here. If our triangle uses those points, we can just think of our triangle as belonging to 3 different lines. Instead of thinking of this side as the side of a triangle, let's think of it as the side y equals 1. Instead of this being a side of the triangle, we can think of it as the equation y equals x minus 1. And instead of this being the side of the triangle, we can think of it as the vertical line, x equal 1. So saying that this triangle forms the border is equivalent to saying these 3 functions form the border. So we've adapted for the triangular description. So let's treat this as our borders, and let's apply our normal process. We want to identify, is it dx or is it dy? And we want to identify if these are washers or circles. This case is a dy problem. And the reason it's a dy problem is our axis of revolution is a vertical line. The y-axis is vertical. Any vertical lines are going to be dy problems. We also know that this is a dy washer problem. What makes it a washer problem is the y-axis, also known as x equals 0, is not a border. These 3 equations represent our border. None of them are x equals 0, so our geometric slices are going to be washers. And our integration is going to be dy. Now that we recognize dy integration, it's a good idea to take any function that uses x as the variable and rewrite it as a function that uses y as the variable. So y plus 1 is really how we want to think of this linear equation, because we're going to be doing dy integration. And so we slice. And each slice is a washer, so each slice has the property pi big R squared minus little r squared. In order to approximate, we need to go back and identify what is the outer function and what is the inner function. If our axis of revolution is the y-axis, that means that this line, x equal y plus 1, is the function farthest away from the axis, so this is the function that determines big R. Big R of y is always outer minus axis. In this case, our outer function, if we use y as the independent variable, is y plus 1, and our inner function is x equals 0, so minus 0. Y plus 1 represents big R of y. Little r of y is always inner minus axis. If we look at where our axis of revolution is, the inner, or the closest function is this vertical line defined to be x equals 1. Mr. Hawks is making an announcement. Mr. Hawks is still making an announcement. Okay. I'm excited that Mr. Hawks made that announcement. because now I feel like this is just like a real class. So we left off saying inner minus axis. We looked at this as our axis, and we looked at this as our inner layer, x equal 1. So x equal 1 minus axis gives us x. Oh, I'm sorry, I need to redo that. X equal 1 is inner, minus x equals 0 is outer. So our inner radius is actually the constant function 1. This makes sense because if we rotate around the line the y-axis, the line x equals 0, what we get is a small radius that produces a small shell, and a larger radius that produces the other outer layer of the washer. And it's pretty clear that from here to here, 1 is always going to be the value of that smaller radius. So we're comfortable with that result. Instead of big A of x, we have a big A of y. And we still just want to take A and substitute in big R, which is y plus 1 squared, minus little r, which is simply 1 and then squared. This actually simplifies well, because the quadratic is easy to expand, y squared plus 2y, and then we'll have a plus 1 and a minus 1. So let's represent that as the most simple version of A of y. The volume is the integral of A of y dy. It's important to remember that if y is the variable, we look at the y-axis for our A and B values. Pretty clearly, y equals 0 is where the area starts, or where A is. And then y equal 1 represents where the values of y stop, or our B value. So we have 0 to 1, A of y dy. This could be evaluated with antiderivatives, factor out pi, and then just 2 simple antiderivatives. In the interest of time, let's just say that this represents our volume, and this is our main goal, writing an integral expression to capture volume. That's number 31 from page 392.